everyone. So let's today I'm going to continue my talk about the convergence. So so last time we talked about, so we are at the problems where we are trying to solve for the lattices. So so basically, I was trying to find, yeah. So I was trying to so the very big problem. So so the big problem is to like to find where so if we have the lattices, so basically I want to find the summation, so find the convergence, so show the convergence of the sum of over all like the over all omega not equal to 0, where we have the omega 1 over omega squared. So where this omega is equal to n1 omega 1 plus n2 omega 2. So maybe omega not equal to 0, 0. So we are under the special case where the omega 1 lies in like the real number, and also the omega 2 lies in the imaginary real number. Sorry, the real positive number, imaginary real positive. And then we also use the idea that we also under the situation where the lattices, it has break into 4 quadrants, right? So we have already shown some symmetricity of the left 2 quadrant and the right 2 quadrant. So we show that the sum of the left 2 quadrant is equal to the sum of the right 2 quadrant. And then, so we also show that, and then for the lines, for the points lying on the real and the imaginary axis, we just ignore them for a while because the sum is always finite, right? So because here, when we sum over the 1 over omega square, where the omega is like a real number, therefore it will lies. It's just like the 1 over n squared, right? So therefore it must converges, and the same thing for the imaginary number. So we just ignore them for a while, and then for the lattices here, so we also show that the top and the bottom one has the same value. So here we just show the top one. Okay. So also the first quadrant, I think it's quadrant, right? And the fourth quadrant have the same sum. Yeah, I think I showed that. Okay. Yeah, I think I showed it before. So now we just focus on the sum of the first quadrant, right? So, some recall. Yeah, some recall. And then, so for the first quadrant, so we have already, so for the first quadrant, right? So therefore we focus on the sum of the first quadrant. So therefore focus on the sum of the first quadrant. So now, what we want to do is that we want to find the sum for of the first quadrant. So yeah, so this leads us to the simplification, right? So our calculation before, okay, so our calculation. So maybe our previous calculation. So basically, like the expansion of the real and the imaginary parts have shown that the sum of the first quadrant is exactly the same as the sum of the points in the first quadrant. Is the same as yeah, so it's the same as the sum of this one. So the sum of some of the lattice point. So I think we have the lattice point here. So we have the double sum. So n from 1 to infinity of summation L from 1 to infinity. So summation J from L from 1 to infinity from like L minus 1k plus 1 to k minus 1 of, oh sorry, let me put it here, nk square minus j square over b square nk square plus j square squared. Yeah, so this is someone here. So let's see where I. Okay. And then what we have is that so this lattice basically is just and also under the assumption that this modulus of omega 1 is equal to k modulus of omega 2. So and then so this is like k. So this is like j equal to k, and then so this is like j equal to. Oh, sorry. This is oh yeah. So we are So this is like that, and then all the way through here. Okay. And then last time we showed that so in order to show the convergence of this guy, right? So basically, we want to use the barrier argument, right? So to show the convergence of this guy, we use the barrier argument. So the barrier argument says that for the point that lies in the barrier with the distance L, so the barrier argument says that so if this L is less than K, right, where no points is being omitted, so this implies that so the sum over the L is equal to so let me write it here. So it implies that the sum of this L is equal to, so it has 3 parts, right? So the parts where, so let me see like here, maybe this is L. So the parts where, so these are some points here, some points here. So the parts where, so for a fixed J value, right? So where the J value is equal to L, and also the N value is equal to L until the corner points, and then plus the corner points. Okay, so so here, let's see, it has 3 parts. So maybe so when J equal to L, so we are summing over all the like different n's from 1 to L minus 1. So n from 1 to L minus 1 of this. So here we have the nk, right? And then so nk squared minus. So this is J equal to L. So L squared over have b squared times this nk squared plus L squared, and then plus summation m from 1 to. So now we fix n equal to L, and then sum over m from 1 to L minus 1 of the sum. So it should be Lk squared minus m squared over b squared over L times Lk squared plus m squared. Oh, sorry, I think it should be a like bracket here, and then plus the like the corner points. So which is the where J equal to L and n equal to L. So Lk squared minus L squared over b squared times Lk squared plus L squared. And from here, we analyze the summand here, right? So basically, for the denominator, we can find a common lower bound. So it is true. We can use a lower bound for the denominator estimate, and also for the numerator. So to the numerator, basically after we find a common like a lower bound denominator, so we just sum over the numerator, right? So for the numerator sums, right? So the numerator sums, I use the letter the numerator of a to denote the sum of the numerator, and then here I use the sum b of the numerator, sum bn here. So and then we from last time I showed that. So last time, so I showed that. So showed that we have the sum over a. So let me just call this a here. and then put b here, and then sum over all a the numerator part plus the sum of the b numerator part is so let me write it here. So it's equal to so 2k squared minus 1 plus k squared minus 2 times L cubed plus negative 3k squared plus 1 minus plus 1 minus k squared plus 3 L squared, and then plus k squared minus 1L k squared minus 1 times L. Yeah, so let me see here. Okay, nice. So So now, so now I want to sum over the, and also I want to sum over the corner points, right? So, so now we sum over the corner points. Yeah. So, so when we sum over all the corner points, so yeah, I have to erase this one. So so maybe just erase this part. So therefore we have so sum over a numerator plus sum over b numerator plus the corner point. So the numerator for the this one, and then we get so if we sum over this one, right? So what we have is that so we have the L squared k squared, right? So L squared k, so this cancel out with the negative L squared k squared, right? And then I have a negative 1, so I think it's cancel out with positive 1. So so here we have so 3k squared minus 3 times L cubed plus, so this is minus 3k squared plus 3 times L squared plus k squared minus 1L so now So let me find that lower bound for the denominator. So lower bound for the denominator. So I have that the nk is so if I fix an L for the horizontal line, if I fix L, like I look at the like the row with the j value equal to L, and then if basically let's say fix j equal to L, and then we know that so in this case, right? So then the set of denominator is given by the set of, so here I'm just copying this term here. So right, so here I'm fixing m equal to L on the set A, and then I'm letting n goes from 1 to L minus 1, right? So let me just also include n equal to L also, such that the corner points. So in this case, what I have is that I'm having the set of where the denominator is exactly given by b squared times nk squared plus L squared, and where this n is from 1 through L, right? So in this case, I want to figure out what is the lower bound, right? So the minimum element. So let me use the letter AD to denote this one. So let's call this AD for the denominator. And therefore the minimum over the set AD is equal to exactly because the smallest one among all these points are exactly the point where this n equal to 1, right? So we can check that this point is actually less than or equal to any other element in this set. So it's equal to exactly the b squared times n equal to 1. So k squared plus l squared squared. And then, so, yeah, I want to keep this one, so I have to erase this part. So, okay. So, yeah. So similarly, so I have that. So now I want to work on the denominator for the set B. So we fix n equal to L. Then the set of denominator is set of denominator is given by the BD, which is being defined as a set of b squared times. So now I'm fixing the n equal to L, and then let m runs from 1 to L. So here this is L minus 1, so I'm also adding the corner point. So b squared times lk squared, then plus m squared, and then where m runs from 1 to L. So in this case, so we have the minimum of this set, so which is equal to, so it's like the element that's less than or equal to any other element, so which is given by m equal to 1 times lk squared plus this is 1 squared. So now for any element, so now I want to find the global minimum among this L, right? So to find the global minimum, so what I want to do is that, because I want to show that I want to show that so the global minimum is like basically it's an element. So basically I know that. So basically I want to show that for the global minimum, it must be the smallest one, right? So from the so this is the set A union the corner point, right? So A union the corner point. So roughly speaking, it's A union the corner point. and then so this is like B union the corner point. So to find the global minimum, so the global minimum must be less than or equal to the local, so it must be the smallest element in the set, right? The smallest element in the set must be less than or equal to the smallest element of this set, and also must be and also must also less than or equal to this set, the A union the corner point. So 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 now what we have is that so so let me see. So for the global minimum, so the minimum of let's see over minimum over AD union BD, right? So let's call this LD. So we have that this LD must be less than equal to the minimum of AD, which is equal to B squared times K squared plus L squared squared. And also LD must be less than equal to the other guy. Squared plus M squared squared. So yeah. So then so then it must be one of them, right? Because it can be yeah, it must be one of them. It can be yeah, it can be bigger than both. Yeah. So therefore yeah, so therefore we pick the smallest one among these two. So so which is the smallest one? So this is 1 squared. yeah, so this is bigger. Okay, so because wait, so why do I want to pick them to be the smallest one among these two? So basically for any point, right? So if you pick any point, so either it is in the set below or in the set above, right? So if it is in the set below, then it must be less than or equal to this guy, and if it is in the set above, then it is less than or equal to this guy. So basically, so the smallest one, right? So the smallest one among these two minimum is gonna be the lower bound. The lower bound for this set, and also this lower bound is being achieved, right? So yeah, so this shows that this is actually the minimum among these two. So and then we claim that we claim that this one is the minimum one. So b squared times lk squared plus 1 squared. So it's less than or equal to. So let me delete the b. K squared plus, and also delete the square. So why is true? Because the left hand side is exactly equal to because yeah, I want to keep this one. So yeah, so the left hand side is equal to so sorry, I have to write here. So the left hand side is equal to L squared times K squared plus 1 over L squared, right? And then the right hand side is equal to L squared times K squared over L squared plus 1. So yeah, because so the K squared is definitely bigger than the K squared over L squared, right? And then if K is bigger than or equal to 2, then and also L is bigger than or equal to 2. So then K squared over L squared is definitely less than, bigger than 1, I think. Well, no, like bigger than yeah, so it's like so it's like the K squared over L squared. So it's like the so it's like so we can write like the think of the k squared as, so think of like the you can split the k squared, right? So yeah, let me think. So yeah, it's a little bit messy. So yeah, so maybe I exercise. Okay, so maybe I exercise. So show that so this show k squared plus 1 over L squared is bigger than the k squared over L squared plus 1. Okay. So therefore, so this is the global minimum. So oh, sorry. So which one? yeah, this one is wait, sorry, I really feel sorry. So actually I think it's like reversed. Yeah, so this one is minimum. Yeah, so this one is the minimum one. Yeah, so yeah, so sorry. So yeah, so this one is the minimum one, and also so and also we pick the minimum one to be this guy, and then so therefore we get the result that so this shows that so this shows that so we have this guy, right? Yeah, so this shows that the sum of over L, so which is this sum, is less than or equal to because here for the denominator, right? So the denominator can be because this one is a lower bound for the denominator, so therefore each of the denominator must be bigger than this one, right? So therefore the whole fraction is actually less than or equal to this one on the denominator, right? So with the numerator the same, so it's less than or equal to. So so for each of the denominator, I replace them by the just the L squared times. So here this one is just like the k squared plus L squared, and then times the sorry, this is like I feel like I'm deleting one. Wait. So this should be b squared, yeah. So originally I deleted at b squared here, right? So originally I deleted b squared. So here, so it should be b squared times k squared plus L squared. So I don't think there's L squared. Yeah, so this is like b squared, and this is a b squared. Yeah, and also I also remove the square. I just because compare this. Yeah, because I just compare the inner part of the inner square. So this is squared, and then for the numerator. So I know that I sum over the numerator. The numerator is like keeping the same. Plus this point here, LK squared minus L squared. So which is equal to so this guy, right? So here I get the sum for the top, so which is 3k squared minus 3 times L cubed plus negative 3k squared plus 3 times L squared plus K squared minus 1 times L over E squared times K squared plus L squared squared. Okay. All right. So yeah, I'll just pause here today. So this is our conclusion today. So next time I'll just continue this argument. Next time I will discuss the general situation where this L is maybe equal to K or bigger than K. So next time. Situation where L equal to K and also L bigger than K, and also analyze the series, the sum over all else. All right, so let's stop today, and yeah, see you next time.